Hello, welcome to Error Lecture 3. So if you're watching this, you should have already seen Error Lectures 1 and 2, and you've probably also seen the calibration lectures. Although if you watch this lecture without watching the calibration lectures, everything should be fine. This shouldn't really, this shouldn't depend on those lectures at all. Okay, so what we want to talk about in this lecture is the idea of error, which we've developed in past lectures. So we've already said for any measurement x, so if x is a measured quantity, like so I go out and measure the length of a blade of grass in my yard, let's say, it's a measured quantity. There is, we theorize, we imagine that there is some actual value out there in the ether that we wish to approximate, but that our attempts to determine that actual value are frustrated by sources of error in our measurement. Now, error we categorized so far into two different broad categories. One of them was random, and the other one was systematic. Good. So remember, systematic error is the deterministic one. It's the one that whatever random is, systematic is not that. It obeys patterns. It is predictable. If we could just understand it well enough, we could predict it, right? We have hope of doing that. So for example, I brought up in the past lectures, systematic error was remember that was the parallax error. Well, I'm short, so I might be looking up at a gauge, and because of my angle looking at the gauge, I might accidentally read a needle incorrectly, right? So that was an example of systematic error, where every time I take the measurement, that error is going to be there. And there are other forms of systematic error. Let's say you've got a sensor that uses strain gauges, and you calibrated it on a cold day, and now you're out in the field and you're taking measurements on a hot day, and your characteristics have moved and you haven't realized it, right? So that would be an error in your calibration, for example, would show up as systematic error. You'd see a similar error, at least a pattern of errors, in every measurement. And the big deal was, the reason we really wanted to wrap our head around that difference was, in the systematic error case, oh boy, that is not true. In the random case, though, what we said was when, we said this was true. Wow. So when n gets, that is the number of samples, becomes very large, we can expect this. And keep in mind that xa, right, is not a random quantity, right? So the error here can have parts, components, contributions that are random and contributions that are systematic, and we will organize those into two separate parts. So when the measurement is purely random, this is when we get to do that. In real life, you've got both of these kicking around in there, so that's even messier. Okay, but for now, as we begin our study of error, this is what we'll do. Okay, so that's great and all, but now that we're talking about this, we need to get deeper into what happens in real life, but n is finite. What happens when n is finite? Because that's real life. That's the world in which we live. For that, we need, if we're going to characterize things that are random, just math, well, the tools of mathematics are certainly going to be needed, but in addition to that, we're going to need statistics, right? Now, you will have already seen, many of you will have already seen and be familiar with the concept of probability. I'm going to go ahead and reintroduce it. For some of you that may be helpful, for some of you it will be terribly boring. Well, oh well. So what is probability? We need to talk about what are the chances that we hit close. If things are random, then we can't just rely on things working out. There's a certain probability that things will work out a certain way or not. So we need to understand what is probability. That's going to be a tool that's helpful to us in this conversation. So what is probability? So here we would say in a context, we'd say that what is the probability of a statement, or rather a condition, excuse me. Another way to read this, and here's what's frequently left out of this, is the context in which we ask the question. Let me talk to you a little bit about what I mean by that. So this statement, this mathematical statement, P of something equals a number, that asks the question, for what fraction apparently I can't spell. So let's pick this apart a little bit. So when I talk about probability, what I'm saying is for what fraction of all cases in a given context is the condition true. So in other words, let's give some examples just to try to give meaning to this rather abstract definition. So in a context, let's say, so for For all computers on Penn State campuses, what is the probability that what I shouldn't say is that they are, excuse me, that any one is. So what is the probability that any one is running Linux or Windows? That is, if I come across a computer with a Penn State tag on it and I know nothing else about that computer and I boot it up, which operating system do I expect it to be running, right? So what is the probability that that is a Windows machine? What is the probability that is a Linux machine, right? So this is a question we could ask ourselves, right? So knowing nothing else about that computer, and obviously this is pretty verbose, but here's the context. There's the context for all computers on Penn State campuses. What is the probability? That's the function of writing this capital P here. That lets us. That's a red flag to us that, hey, we're talking about probability. And then here's the condition, or the condition is that it's running Linux. So in this case, the condition is easily testable. You have a way to definitively say true or false. You boot the computer. If it's Linux, it's true. If it's running anything else, it's false, right? You count up all the true cases and you divide them for the total number of cases in the context, and that's your probability. You're done, right? Okay. So just to give a quick example of how much context matters, right? If we repeat this and say, for all computers in my household, what is the probability that anyone is running Linux? The answer is 1. All computers in my household, including my wife's and my, well, hang on. Yeah, no, I guess my kid has some Apple stuff, so we'd have to call that a flavor of Unix. But sir, what is the probability that it is running Windows? Goose egg. 0. There is no probability of a machine in my household running Windows, unless my wife brings her work computer home. Okay, so But you get the point. The point is that the answer to the question changes dramatically with the context of the probability, right? So that is what circumstances do we know before calculating the probability? Now this gets into this gets into some more interesting dynamic. This takes on a more interesting dynamic than just yes or no, or than just Linux versus Windows and me being snarky about software. For example, so for a dice roll or for a die roll, dice. Yeah, dice is plural. For a die roll, what is the probability for a die roll X, let's say? What is the probability that X is less than or equal to, we'll say, 3? Well, so a die roll has 6 possible cases, right? So 1, 2, 3, 4, 5, or 6, right? Assuming a d6 or 6-sided die. So what is the probability that that X is less than 3? True, 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 false, false, false. That is equal to then 1 plus 1 plus 1 plus 0 plus 0 plus 0 divided by 6, or 3 over 6, or 1/2. So these would be 3 ways of representing that probability: 1/2, 0.5, or this is how it's most commonly represented when you read about statistics. It's 50-50, right? 50% probability. Now this, I made an assumption here. The assumption was that each of these die rolls was equally probable, right? And so in reality, we need to. Here's a different way of calculating this. All right, let's do this again. But let's take into account what might happen. Let's say we're in Vegas and we're rolling against someone that's using weighted dice. That's not nice. But let's pretend. Well, so let's look at the probability of each one. So if each one of these had even probabilities, that the chance of every single one of these cases is equal, then every single one of them would have a 1 in 6 chance of happening. That is, you give 6 tries, and each one of these is equally likely to come up. Now, notice that I'm using a little p here, so that's a lowercase p. So this is the probability of each possible case in my system, right? All right, now, so now I can still apply this test. So is this true? Is this true? Yep, true, false, false, false. So here I apply my condition. So here's my context. All my possible cases there. And then here's the probability of each condition in the context. All right, and now instead of doing what I did up here, the way that's going to be more useful to us is to sum up all of the individual cases. So you'll notice that I still end up with a 1/6 here, right? I just summed true, 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 false, 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 divided by 6, right? And I got this result. Well, that's whence cometh the idea of 1/6 being the probability of one of these, right? We borrow that notion from up here. All right, so let's go ahead and add this up. So we only add the cases that are true. So we're going to sum up all the probabilities that meet this condition. So that's 1/6 plus 1/6 plus 1/6, right? Because only 3 of them are true, which is 50%. All right, So this is the idea of probability, right? Half and half. Now, but what if we have a new context, or what if we have a new die? So here in my context, there we go. What if things were a little squirrely? I don't actually remember what number is opposite the 2, but let's pretend things are weighted so the 2 is less probable than, say, a 4. Let's say the 5 is opposite the 2. So let's say a weight has rendered the 5 more probable. Okay. So let's say we've got probabilities that look like this. And our conditions still are true, 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 false, false, false. So the condition hasn't changed, but now we have a different situation. This is that we're rolling a different die, right? So the probabilities have shifted. So if someone's done something nasty with the dice, and now our probability calculation is affected. There we go. So this is a new situation. So that one looks like it's going to be 5/12. That's about, let's see, a 12th is about 0.083, so that should be about 0.415-ish. 15%. Let me write that nicely. 0.415, about. I think so. 41.5%. Pretty sure. I think I got that right. So you can see that by changing the context, we've decreased the probability of this being true, and so what that means is if we have one roll of the die, what is the chance that we are less than or equal to 3? Here it's even odds. Basically, you could have the same outcome with a coin toss. But here it's actually much more complicated than that, and it's less probable than even odds. In fact, more cases will it come up greater than 3 than will it come up less than or equal to 3. That's what we determine here. Okay, so that gives you the idea of probability. Now notice that in this case, what we're concerned with is for a single die roll, that is one measurement, or in our case, right? So one execution of the random task, right? This is what we get. Well, basically what we're playing with here, we just did two different cases. We examined a case, or two different contexts. So here I've got a lowercase p. I'm putting a hash there just to emphasize it's not a capital P, it's a lowercase p. So yeah. So in the first context, if I just try to visualize what was the probability of each outcome, we said that every single outcome had an equal probability. So even chances of everything happening, right? And for the second case, we had a different scenario, right? So in the second case, we said that 2 was less likely than 5. And if for those of you who are staring at a six-sided die, I apologize if I have incorrectly guessed which number is opposite 5, but And in reality, if 5 is weighted, then all of the numbers are actually going to be impacted. 2 the strongest for sure, but all of them will be somewhat impacted. So it's not a, admittedly, it's not a perfect metaphor. All right, so 1/12 is down here, 3/12 is up here. So we can construct this little example where all of a sudden 2 is much less probable than the others. What we are doing is developing the idea of a probability distribution, the idea that there are a whole bunch of different individual cases that can occur, a whole bunch of different individual cases that can occur in our context. Every single one of these is possible in our context. That is, it is possible for the die to come up on one of these values. It is not possible to have a 7. It is not possible to have a 24, right? Those are out of the realm of possibility. So our context only permits these values. Then we say each value has a certain probability. We call that little p, right? That's the probability of an individual case occurring, right? And then we evaluate those individual cases as to whether or not it met our condition, our statement. So we said, what is the probability that something occurs, right? So every single one of these cases has a certain probability. Half of them met our condition. So right, half of these cases met our condition. But in our last calculation, we accounted for the fact that one of those cases, even though it represents half of the possible cases, one of those cases is less likely. And we visualize that with this little plot here, right? That's the basic idea. So over here, this is a uniform probability distribution. That is, everything is equally probable. And we basically reflected that in our first two calculations here, right? So everything was equally possible. But when we start making some cases more probable than other cases, we see that show up here. Neat. So this introduces the idea of probability distribution, where that your measurement can have some value, right? So it can take on some value, and each of those values has some probability. All right. So what about a measurement? We're dealing in die rolls here, so what about a measurement? Now x could be, well, whatever. It could be a pressure, it could be a length, it could be just about anything, really. Well, if it's a length, I can no longer pretend, I can't pretend with a straight face that my length values can only have discrete values. A length or a voltage especially, right? These can be anything. They live in a continuous variable space. Now we're taking digital measurements, so yeah, it ends up being discretized eventually. But really, the resolution is so tiny that we can think of things as continuous anyway. So we're going to work in a continuous space. So basically, in other words, right, I can any two measurement values, no matter how close they are together, I can always name a possible measurement value between them. So there is no smallest resolution here that I could break this kind of a plot up and call it good enough. I could always break it up smaller. Yes, ladies and gentlemen, that is the stuff of calculus. We're going to need calculus for this. So instead of there being discrete values with probability, instead, no, we will have ranges of probability. So what if I instead, for a given value of x, what if I imagine some itty bitty range on either side of of x, and we call that width dx, right? Well, then p, probability, that's lowercase p, the probability there is going to be such that need a name for this. I'm going to call this x1. Oops. Well, I just made a hash of that, didn't I? Silly me. Sorry, let me try that again. What is the probability that x is greater than x1 minus dx over 2? And there is better notation for this, but we haven't learned it, so I'm not going to use it. So what is the probability that x is greater than this little limit here, and that x is less than So in other words, what's the probability that x is in this little tiny range? And then if I say, well, this is little p. And I can repeat this. I can repeat this experiment as often as I want, and I get a function, little p of x. This is called a probability So I forgot to multiply by dx there. So basically, as dx declines to 0, as dx goes away to 0, the probability, so does the probability. Probability goes to 0. Not probability. The probability times dx, or excuse me, divided by dx. So this whole thing divided by dx does not go to 0. It converges, just like a derivative. In fact, what is the probability that x is less than x1? This is equal to the integral or So, in other words, you can think about these density functions, these probability density functions. So we started with discrete values, where every number only existed at a single point along the line. Well, this is just a continuous version of that. So now little p, and we calculated total probability in the range we were interested in, say like this. Right? We calculated that value by summing up all the probabilities in that zone. That's exactly what we did, right? Well, this is going to be the same, only it's a continuous version of that. So in other words, right? So if I could imagine a probability density function, this is probability per little dx that I include in my region here. The probability per x that I include. So if I imagine that this probability density function, then the probability that I am in, as long as dx is very small, what we said was the probability that I'm in this region right here is p of x times dx, right? Times that width. It's the area under the curve. It's summing up all the little area in there. Now, if I wanted to expand this to include a larger region, like everywhere left of x1, right? That would need to be the area all under this region here, right? And so that would be the probability that x is less than x1. I don't need to write it again. I've already got it. It's right here. It would be the sum of all the little probabilities in that region, right? Now the idea is, again, that the little probability, that is at just this point here, is the probability density at that point times the differential width dx, a tiny, tiny width of probability. This raises a really interesting and for some deeply troubling idea. So what is the probability that if I go out and measure a blade of grass, what is the probability that the answer will be precisely 1.73942 inches? Now, I mean precisely. What's the probability it will be exactly that? The answer is 0. There is, in fact, no probability that any blade of grass in my lawn. I have a lot of blades of grass out there. They're exhausting to cut. So there are a lot of blades of grass out there, but the probability that any one of them is precisely any length vanishes to 0. I mean, there is no probability it will be exactly that length. There is, however, a finite probability that a blade of grass will be between two lengths. Basically, you have to have a finite window of values to accept. So the probability that x is equal to x1 is equal to the integral over an infinitely small band is infinitely small. It's 0. So whereas the probability that, now here's a nicer way to write it. Beautiful. Well, that looks pretty good. And that is not equal to 0. So now, so far, we haven't made any assertions. So we've defined what is probability. We've got a loose idea of what is a probability density function, or PDF. Let me actually, I haven't actually written that. I've said it a couple of times. Let me actually write it. So this is the probability called PDF in a lot of circles. So what is the, and that these are little p, right? So that's little p, there's capital P. So yeah, the probability, we have made no assertions about the shape of the probability density function. We've talked a little bit about how to relate it back to the probability, and we've done some examples when with discrete cases, right? When in the non-continuous world where numbers can have only integral, like integers, that is. Okay, so not bad. Now, there are a couple of restrictions we need to put on probability density functions. And those restrictions, believe it or not, we've been obeying, just we haven't lent language to it yet. So if I go back to this example, go back to the discrete case, right? Notice that if I sum up all of my probabilities, I get 1. That is, in other words, what is the probability that my dice roll is less than or equal to 6? Well, given a context, what is the probability that I'm in the context? The probability has always got to be 1. You've got to have the answer of what is the probability that you gave that the context is realized. Well, 1, you told me the context is true, so I know that's true. I know I'm in a number from 1 to 6. That was part of the context. So the probability that I have a number from 1 to 6 has got to be 1 when I use this method. And sure enough, it is. So that's why our probability was 1/6. So here it's pretty obvious. Here it's less obvious, though. Here we start monkeying around with the probabilities. What we see is if you add probability to one case, if you make one case more probable, that had to come from somewhere. Some of the other cases had to become less probable. Otherwise, they wouldn't have all summed up to 1, right? But you'll notice if I take 3/12 and add it to 1/12, I get, yeah, that's right, 4/12. That's right. So I get 2/6 or a third. That's right. So basically, the sum of 2 and 5 I just conserved, right? That's why I did it that way. So this also sums up to 1, right? So I need a similar constraint here when I'm dealing with probability density functions. So what is the probability that the probability that x is a number is 1, right? I may not know much about x, but I hope I can say that much. I guess I could ask the probability that x is purple, but that's outside of my context, is the point, right? So that, yeah, probability that x is a number is 1. So in other words, that actually gives us a constraint that must be observed by all probability density functions, is when you integrate them over the entire context, that is the entire range of possible values, they must integrate up to 1. So the probability that x is in the context is always 1, right? So that's a hard constraint. Well, so most of you have heard of normal distributions. So or the bell curve, right? So the normal distribution, a Bayes' law, something like this: probability of x, probability density of x is let's see if I can remember this. It's been a while. Okay, what it says is that the probability density function has a certain shape to it. Now, that shape is centered on, is centered around what you will recognize as the mean and has a width let me add a subscript of x just to emphasize that's on x. Oh, and you know what I forgot? Yeah, so I just double checked my my probability density function with my handy dandy search engine, and realized I forgot to divide by. There's a 1/2. Oh, idiot! Yeah, I forgot a negative too. There's a negative 1/2 up here. I forgot. Oops. Sorry about that. Okay, so yeah, basically it says that, and this is probability density of x, right? So what it says is, now remember, probability density. So if I consider ranges, so windows of measurements, very close to the mean, the area in that range is very large, right? So I have a lot of probability of being close to that mean. But the farther and farther I get from the mean, the less and less likely it is that I'll get something there. For example, if I have scored a 72 on just about, or 72, a 71, a 68, and a 52, let's say, on all of my last quizzes, the probability that I will score, if I know nothing else about the subject matter or my performances, the probability that I will score a 99, somewhere between a 95 and a 99, is out here, right? So the area, it's still possible, it's absolutely possible, but the area under that curve would be small, and so it's unlikely. It's always possible. It is always possible. It is just it is merely unlikely, given what we know about past performance, right? So the normal distribution has a number of it's a bizarre formula, right? But it has a number of amazing properties. First of all, so it is symmetrical about x. You'll notice if x is about x bar rather. You'll notice that if x is smaller than x bar, you get a delta here, and then you square it, right? And it doesn't matter if it's positive or negative, right? So it's symmetrical about x bar. Of course, the reason for this complicated denominator here, that's a normalizing coefficient to ensure that the integral of p of x everywhere is 1. Right, that's the reason for this irritating coefficient. And you'll notice that its shape is completely determined by two parameters: the mean, right, and then the standard deviation. So this is the normal distribution. So if you wanted to know the probability, so if I had a system with, or let's say, of 4.55 inches, maybe it's a length, who knows, of 4.55 inches, and a standard deviation, so this is x bar, I'll call it, standard deviation of, I don't know, let's call it a 16th. What's the probability that x will be less than only 4.5 inches? So in our case, we would be looking at so here's my mean, and let's see, I am 50 thousandths off to the side, so I'm here, let's say, and I'm less than a standard deviation away. So if I actually plotted this, I suspect it would look something like this. All right. So the probability that this occurs, what is the probability that x is smaller than this? the probability that one of my measurements returns that value. Now notice I haven't said anything about actual values. I haven't said anything about error. I've just said that, hey, if I take a huge population of measurements, having told you nothing about what they are or what they mean, they tend to come back with a probability distribution that looks like this. It's a bit of a lumpy sketch, so apologies for that. So if I just ask you a question, what is the probability that one of my measurements is less than 4.5? What we need to do is calculate the area under this curve. So the probability that a measurement comes back as less than 4.5 is the integral from negative infinity to 4.5 of p of x. There you go. Now, next time, I'm going to stop the lecture here. Next time, we're going to figure out how to do this. Most of you have done this before, so next time I'm going to come back and figure out how to actually look that up, right? So this is not an easy integral to take, as you can figure from looking at it. But so yeah, we'll use tables. Hooray! Okay, thanks for watching.